Okay. So I'm going to share my screen, if I can find the screen share. Share screen. Okay, beautiful. Hopefully you all can see my WIO courses page here. If not, somebody just let me know. Okay, so when you go into the trigonometry course shell, this is what you should see. There are 3 modules here that will be very important, especially in these first couple of weeks. We have the start of the semester stuff, which is all of the things with Alex, which I will talk about in a minute. We have the common links, which is how you will access Alex, the classroom Zoom link. Hopefully that's how you all got here today. And just the syllabus, which we will be going over. And then office hours, you can access that link here, as well as recorded Zoom lectures. This will be the page where after every single class, I will post the lecture under the day it happened. So after today, I will put the lecture for July 5th right here. Okay. So first things first, I know many of you already have done this. Thank you to those who have. But getting started in Alex, if you have not done this yet or looked at this page, you will need to do this by the end of the day today. You cannot do any work really in this course until you look at your Alex and get that set up and do your initial knowledge check. So if you have not done this yet, please read this page and watch this video when you get a chance. An old instructor made this video. It is old, but it's still helpful. Alex has not changed their software too much in the last few years. So any FAQs will be answered here, but essentially this just tells you how to sign into your Alex account, get that set up. And Alex is where you will be doing all of your online homework. If you've taken college algebra before through the university, you may already have experience with Alex. So hopefully things should look pretty similar. And then once you have your Alex account set up, you will need to do something called your initial knowledge check. And essentially what this is, those of you who've already taken it probably know this, but it kind of serves as a pre-assessment / starting point for you in the course. It tests you on some of the topics in the course, sees where you're at, where your understanding is. This is just for participation. I can see if you've done it. And once tonight is over, because it is due tonight, I will just give everyone who has done it the full 30 out of 30 points. Does not matter how you did on it. However, I do encourage you to do your best, because the better you do now and the harder you try now, the less work you will have to do later. And I will explain what I mean by that in a second. But by the end of today, you need to have your Alex account signed up for. If you have any issues with that, please email me. I know it can be a little difficult sometimes. So if you have any issues, just let me know. And then once you get in there, it will prompt you to take your initial knowledge check. That is all you need to worry about for today. Any questions on that? Okay. And if you need more help with Alex after that, there's this page called Getting to Know Alex. The software can be a little non-intuitive sometimes, and I recognize that. So these are some tutorials from McGraw-Hill and from other instructors about how Alex works, why some topics are locked, why some topics are locked initially, what a knowledge check is. And I will explain what all of this is today too, but if you want to refer to it again, or you're still confused, there's a bunch of help and resources here. But all you are required to do for today is just get started in Alex. Okay, speaking of Alex, every time you access it, you would use this link right here. Do not just Google Alex and try to sign in that way. It will not be connected to this course. It will not be connected to your UW account. You need to use this link right here. Classroom Zoom link, this just makes it easier. Of course, you can go into Zoom, and on the syllabus, I have the meeting room number and the passcode, but you can always just use this link as well. Syllabus is here. We'll be going over this in a second. Office hours Zoom link. My office hours will be Wednesdays and Thursdays immediately following class. So you can just stay in this meeting if you would like. It is the same meeting room. However, you may also just use this link. And then, like I already talked about, after class every day, hopefully fairly soon after, within an hour or two, I will be uploading every single lecture, because I know it is the summer and people are very busy. So it is always good to be able to have lectures in case you can't make it to a class, or, hey, I don't remember how to do right triangle trigonometry. You can go rewatch that lecture. So those are always helpful. there any questions so far? Okay, well, if not, we will get into the syllabus, which should just be linked here. Okay, beautiful. Hopefully everyone can see that. Okay, so this is some stuff you already know. Class meets every day, Monday through Friday, same time, 10:30 to 11:50. We will meet via Zoom. This is how you will sign into the meeting through your Zoom account. Here's the direct link if you would just rather do that. Office hours are Wednesday and Thursday immediately after class for an hour, but if these don't work, I'm always open to appointments. I'm pretty available pretty much anytime. So if you need some extra help, I am always here. Just shoot me an email and we can work something out. Okay, so prerequisites, you're all here, so I'm assuming you have the prerequisites. Required material. There's some kind of unfortunate circumstances with the required material and the bookstore right now. Some of you have already emailed me. Currently, there's this book in the bookstore listed. I think it's called Understanding Pre-Calculus or something. That is not the correct book. I don't know what that is. I don't know why it's there. Please do not buy Understanding Pre-Calculus or any other book other than the course packet. I do not believe the course packet has been uploaded to that part of the bookstore yet, let alone I don't even think it's available for purchase. I have been trying to get that worked out. But unfortunately, it's not there yet. I will let you know as soon as it is because the course packet is required. If you took college algebra, you may have had a similar one. And if you did take college algebra in that way, you know that that is where the notes are taken. And so it is very important to have. I'm so sorry it is not there yet, but I will keep you posted. That is the only thing that is required. It will be $30 and I will let you know when that's there. There is, if you look in Alex, there is a textbook listed there called College Algebra and Trigonometry. You can purchase this if you would like. It is absolutely optional. It would just be as a resource for you to have because some people learn by reading. So if you learn math best by reading, this may be a good option for you, but it's absolutely not required. I will never assign problems from it. I will never assign readings from it. That's just a tool for you if you would like it, but don't buy a textbook at this point is moral of the story. Okay, I will skip goals of Math 405. You all can read that later. But grades and student expectations, grades are fairly simple. Your work in Alex will be 20% of your grade, and I'll explain how that breaks down in a minute. Your written work, which there will be a written homework once a week, that will be 20% of your grade. And then there will be 3 exams, each 20% of your grade, in addition to an optional final exam, which I will explain a little bit more how that works. But essentially, the final exam will be if you are unhappy with any of your exam scores, you will have the option to take the final to replace one of those poor exam scores. So say you got a 60% on exam 2 and you are not happy with that, you could take the optional final, maybe say you get an 80 on the optional final, and then that 80 would replace the 60. Again, I will get into that more once the time comes, but just know that that's there. And otherwise, the breakdown is pretty simple, just into 20% each. Any questions so far? Okay. So exams, it's pretty difficult to do synchronous exams over Zoom. We all know that through COVID. It's a pain. Proctoring softwares are a pain. So I'm not going to do that. We will be using the honor system for exams. You will just have the entire day, the day of the exam. So for example, your first exam will be next Friday. There may or may not be class that day. And if there is, it will be a review session, but you will have that entire 24-hour window to do the exam. The exam will be completely written. There will not be an Alex portion. It will be an entirely written exam that you will have, I believe, an hour-and-a-half window within that day to take. So once you start the exam, you will have 90 minutes, but you have the entire day to take it. So you could take it at 4 a.m. if you wanted to. You could start it at noon, but once you start your time, you will have an hour-and-a-half. And you will be allowed a 3-inch by 5-inch index card of notes, which I recommend just because the act of making an index card is sometimes the best way to study. Okay, Alex. So Alex is a little confusing, so I will explain how this works hopefully well enough. And if you still have questions, we can talk about them. So if you took college algebra, you may already have experience with this. Essentially, you will be doing two things in ALEX. One of those things is a knowledge check, which some of you have already done with your initial knowledge check. And the other thing is topics. So topics are just, you will complete a certain amount every week. I think there's like 7-ish topics on angles and radians that are due in a couple days, which is what we will start teaching today, hopefully. And those are just something you do to work through practice problems for the topic you've learned. You will need to get 3 things correct for each topic. And at the end of the due dates, each topic you learn by the due date, you will get 2 points for. So say if there are 7 angle and radians topics, and you learn all 7 of them by the due date, you will get a 14 out of 14 for angles and radians. In addition, you will get 2 points for each topic you master at the end of the semester. So what is mastery? Well, when you get a topic correct on a knowledge check, you master the topic. You can lose mastery, however, if you get the questions incorrect on knowledge checks. However, you can regain mastery by getting them correct later. You can read this, that may help it make more sense, but essentially you will get 2 points for completing the topics on time. Just doing it, it's fine. Knowledge checks, you will get full credit for just for completing them. They are for participation. However, I encourage you to do as well as you can on them, because the better you do, the less work you will have to do later. That's what it's saying here, because you can lose mastery if you do poorly on a knowledge check, and then you will have to do more work later to get that mastery back, because if you lose mastery, you will need to go and redo the topic again. Essentially, the point of ALEX is just to repeatedly keep testing you and quizzing you and checking your knowledge to see how you're doing on the work. So at the end of the semester, you will get 2 points per topic you retain mastery of. So say there's 100 topics total and you have retained mastery of 86 of them, you'll get 86 points at the end of the semester. This kind of makes sense. It may help too just to read this part of the syllabus later. There will usually be about 2 ALEX assignments per week. I think there's 2 this week. I think there's stuff on the angles and radians, and then right triangle trigonometry. I will go and check that after to make sure. But there will usually be about 2 assignments a week. Oh, and also at the right before every exam, there will be something called a second chance assignment. And what that is you will be able to go back into your ALEX and make up any of the topics from that unit that you didn't do. So say you didn't do a couple topics in angles and radians, you will be able, once the second chance assignment opens up at the time of the first exam, you'll be able to go do that and get your points back. It sounds a little confusing now. It may also help to go poke around the ALEX software a little bit. Hopefully this kind of makes sense. Essentially, just make sure you're doing topics when they're due. Make sure you're doing as well as you can on your knowledge checks to maintain your mastery. And if by chance you don't learn all the topics by the exam, you will get the chance to go and redo all of them when the second chance opens. So there will be the first second chance assignment will open next Friday, which is the day of the first exam. And you will have Friday through that weekend to go in and learn all of the topics if you missed any. Hopefully this makes sense. Are there any questions at this point? Charles, you raised your hand?
Yeah, can you hear me, Sydney?
Yes.
So the ALEX portion here, is that considered the written assignment, or is that something
nope,
separate?
That is ALEX.
Just ALEX, okay.
Yep, written work will be separate.
Okay, thank you.
Yep. Okay, yeah, and the knowledge checks in combination with the topics, participation in knowledge checks, learning your topics on time, and retaining mastery of the topics by the end of the semester, those 3 things combined will comprise your ALEX grade. And the details of that points are listed in the syllabus. If you're curious how the exact point breakdown is, it'll make more sense the more we go through the semester. But yeah. Okay, written work or other work. Some of this is a little outdated from the in-person class because we are meeting for 6 weeks over the summer versus 16 weeks in person during school year. This will look a little different. There will likely not be regular activities because we just don't have time for that, but there will be a weekly written homework assignment. It will just be, I think this week's is already posted. I believe it's 4 problems that will just go over some of the stuff we do in lecture early on this week. These shouldn't be too bad, but they will just be written homeworks that you print out, do your work on, and then upload a PDF to WIO courses. If you're not familiar with the app Cam Scanner, that is a great way to turn written work into a PDF. You just take your phone, take a picture of it, and there's even a way through that app to upload it directly to the assignment in Canvas. I can help anyone with that if they need help, or if you have a better way of converting written work to a PDF, great. But yeah, written homework, you'll have 1 written homework a week. These will be due on Fridays, and they will be 20% of your grade. These are for correctness. These are not for completion. These will be graded based on the presentation of your work, how correct your answer is, and the work present. Homework turned in without work and just an answer will not be given credit, per usual in a math class, because showing your work is the most important part. But yeah, so that is written work. That will be 20% of your grade once a week. Pretty typical homework, pretty self-explanatory, hopefully. And I believe the first one is posted. I will check to make sure, but okay. Are there any questions on this? Okay. And yeah, I've already said this, but just to state it again, because I know people have had questions on this, Zoom lectures will be recorded and uploaded. So if you miss class, you will always be able to just rewatch the lecture. Again, even though it is online, I know it's more of a disconnect, but your classmates can also be a very valuable resource if you are falling behind. Sometimes having a classmate explain something to you is the best way to get help, especially because resources for math help are a little limited over the summer. The chasm is not walk in person anymore. We don't have the step tutoring in the library. However, there are office hours, and I am free to meet outside of office hours whenever you need. There is still the chasm. However, tutoring is online, but we still do have this. You can visit the website directly through this link, and it looks like this. It just gives you the hours, which apparently are Monday through Thursday, noon to 5. And you can make an appointment via this link. That is just if you've ever visited the chasm. It's just the same thing. The tutors are just online now. So this is still here. If you need it, please, if you feel like you need help, this is a fantastic resource. And then study groups, again, it's a little bit harder to meet people online, but study groups and getting to know your peers is sometimes the best way to learn. So there's that too. Okay, and then these are just the additional parts. I don't think we really need to go over that. Okay. Are there any questions at this point on the course, the WIO courses shell, the syllabus, how grades are going to work? No. Okay. Then let's get into a little bit of math. Then again, I apologize that you all do not have the course packet. I will try to get that out to everyone as soon as I can, and I will keep in contact with the bookstore and telling them, hey, class has started. This is a little bit urgent. Okay, so let's see if I can figure this out. I'm going to stop share here and then go share content. Okie dokie. So we're going to start off with what might be a little bit of a review for some of you, and that's just degrees in a circle. So, let me get rid of my double face. That's annoying. Okay. So, as I'm sure many of you already know, a circle has 360 degrees. That is how most of you have probably learned how to measure angles before, is in degrees. And for most circles and for most instances, measuring to the closest degree is usually good enough. We don't really care about getting too specific because a degree is really small. Like if this is 15 degrees right here, 1 degree is probably really small. We don't really care beyond the closest degree. However, sometimes in more specific mathematical calculations and instances, we do care, and decimals are kind of messy. So we use something called degree minute second form. And this is just a simple conversion. If you've ever taken chemistry, it is just like a chemistry unit conversion. So for example, right here, we have that 1 arc minute, which the unit we denote by this is equal to a 60th of a degree. In other words, there are 60 degrees in 1 arc minute. So if you think of splitting this little guy up into 60 pieces, this guy here, if you think of splitting that into 60 pieces, one of those 60 pieces is an arc minute. And if we want to go even smaller, we think about arc seconds. And 1 arc second, which we denote by 2 little hash marks up here, is equivalent to a 60th of an arc minute. In other words, there are 60 arc minutes in an arc second. So that would be 1/360th of a degree. So this gets really, really specific. Okay, so what is degree minute second form? I will just write down a brief definition. So when we talk about degree minute second form of writing down an angle measure, it is essentially, we are just breaking down the decimal part of a degree measure into minutes. Then once we have done that, we break down the decimal part of that into seconds. Okay, seems easy enough. Let's do an example. So I want to convert 121.719 degrees to degree minute second form. First, we want to break down the decimal part of the degree measure into minutes. So just notice right away that 121.719 degrees is equal to 121 degrees plus 0.719 degrees. Here's the whole number part. Here's the decimal number. We just want to focus on this part here, as we want to just leave the whole number of degrees alone. So how do we convert units? Well, we're starting with 0.719 degrees. I'll just put that over 1. And I want to convert this into minutes. To do that, I know that I need units to cancel. So I need degrees to be down here. And like I already said, I know that in every 1 degree, there are 60 minutes. And that's just using this conversion right here. Each degree contains 60 minutes. So when I do this multiplication, the units of degree will cancel. We will be left with the unit of minutes. And doing this in my calculator, I get that this is equal to 43.14 minutes. Okay, so I know that 0.719 degrees is equal to 43.14 minutes. Okay, I have the measure in minutes now. So what I need to do is break down the decimal part of the minutes into seconds. So now I just want to focus on this 0.14 here, breaking it up just like we did with the degrees up here. We leave the whole part alone because we know 43 minutes will be a part of our final answer. And we just want to see how many seconds that 0.14 minutes is. Same thing. We have 0.14 minutes, and I want the minutes to cancel, and I want to get this in seconds. So I know that for every 1 minute, there are 60 seconds. The units of minutes cancel, and plugging this into my calculator, I get that this is 8.4 seconds. Unfortunately, we don't have a unit even smaller than seconds, so I will not be breaking this down anymore, even though it is a decimal answer. However, our final answer is at 121.719 degrees is equal to 121 degrees, 43 minutes, just using the whole number parts here and here, and then 8.4 seconds. That is your final answer. When you do this in ALEKS, it may ask you to round the decimal off here, but it will, if it does want rounding, it will be specific. But this is your final answer. You just take the whole part of the degrees, which will just be given to you in the problem, the whole part of the minutes, which you will find with this first calculation here, and then whatever you get in seconds, and then that is your answer. Sometimes it will ask you to do it backwards, and it's a similar process, just going from degree minute second form. You will just convert seconds into degrees and minutes into degrees and then add them all. Are there any questions? You may never have seen this before, but hopefully the concept of converting units is at least feels a little familiar. If not, we can work on it. But okay, so a little bit of vocabulary to start off. So by default, angles are in what we call standard position, where the initial side is on the positive x-axis. And all that means, say this is our axis, that means that the starting position, what we consider where 0 degrees is going to be right here. And then the angle can be here or here or here, but the starting ray of the angle will always just be lying right here. That is standard position, and that is mainly what we will be working with in this class. Okay, negative angles and positive angles. So positive angles are when we go around counterclockwise, not clockwise, counterclockwise. So if we, for example, are saying, okay, let me change the color. We want to measure this angle here, and we're saying this is the angle and it's going this way. That is positive. We're going around counterclockwise. However, if we go the other way, that is a negative angle. Just a couple words to know there. Okay, and then coterminal angles. And a coterminal angle is just an angle in standard position, meaning that first ray is just on the x-axis. That have what we call a common terminal side. And all that means is that they have the same ending point. So, for example, you see this one here, angle alpha. This is an alpha, by the way. This is a Greek letter. We will be using this kind of a lot in this class. So just know that this is the Greek letter alpha, and this is the Greek letter beta, the first 2 letters of the Greek alphabet. So angle alpha here goes around. It is a positive angle because we're going counterclockwise and it ends here. And angle beta is a negative angle, goes around, but they end at the same ray. They both end at this guy. So they are coterminal angles. They will have different measures. Obviously, angle alpha is larger than angle beta, but they are coterminal because they have the same ending ray. Same thing here. These both happen to be positive angles. They're both going counterclockwise. However, angle alpha goes to here, angle beta goes to here. They're not the same angle. Angle beta is actually greater than 360 degrees, which we never really think of angles like that, but they can be. However, they have the same ending ray right here. They still end at that point. So they are coterminal. Any questions on any of this vocabulary? Okay, a little bit more vocabulary with angles. You may have seen this before in high school geometry, but I'll remind you again, all complementary angle, oh, whoopsies, go away, please. Okay, all a complementary angle is, or 2 complementary angles are just 2 angles whose measure adds to 90 degrees. So just any 90-degree angle here, any angle that would split this up So if that was the angle and that was an angle, those would be coterminal. Sorry, my lines aren't straight, or complementary. Here, those would be complementary angles. And even they don't have to be within the same 90-degree arc. We could have two separate angles, one of them being 40 degrees, one of them being 50. They would still be complementary because their sum adds to 90 degrees. Similarly, we have something called supplementary angles, and it's pretty much the exact same thing, except instead of 90 degrees, it is two angles whose measure adds to 180 degrees. Are there any questions on these two definitions? Okay. All right, so we've talked about degrees a lot. Maybe some of that was review. If it was, great. And if not, also great. You know it now. But there is another way that we're going to be measuring angles, and that is the main way we'll be measuring them in this class, and those are called radians. If you've never heard of them before, maybe some of you did in geometry, maybe not, that's okay. But radians are another way to measure angles. In radians, instead of 360 degrees, there are 2 pi radians around a circle. So because one full circle here is 2 pi, and in degrees, a full circle is 360 degrees, makes sense that 2 pi radians equals 360 degrees. Now, notice that there's no unit here. That is actually customary, and we'll see why in a bit. Sometimes people would write 2 pi rad. You can do this if you would like. However, just know that whenever you see something like this without a unit, that means it is in radians. You do not have to write units with radians. Sometimes when you're showing your work, it is easiest to write rad just so you can keep track of your cancellations and stuff. But you do not need to worry about units when you are talking about radians. Okay, and just to do a quick little bit of math to make our lives easier when we're doing conversions, because 2 pi radians is 360 degrees, I'm just going to divide both sides by 2. We know immediately that pi radians is equal to 180 degrees. And we can see that in the diagram here. That would be just going around the circle like this, 180 degrees, flat line. Makes sense. Okay. So I will explain more about what a radian is in a minute, but I think it helps just to get a little bit comfortable with doing a couple examples with conversions first, just to get a feel for how they work. So we're going to do an example in each direction, first starting with converting what we're comfortable with, degrees, into radians. So convert 221 degrees to radians. This is just going to be a conversion like we did with the degree minute second form, except we have to do one less conversion. So we're starting with 221 degrees, and we want the unit of degrees to cancel because we want to be left with radians. We know that there are pi radians and 180 degrees. So we want the degrees on the bottom. And for every 180 degrees, there are pi radians, unit of degrees cancels. And then cross multiplying this out, we get that there are 3.857 radians in 221 degrees, approximately. Again, we're working with pi, so which is irrational, meaning it's a decimal that never ends. So your answer will always be around if you do this. You can also just leave the pi in there if you want to. That's okay. But for now, this is acceptable. Usually rounding to 2 or 3 decimal places will do the trick. Alex may have you round to something less or more, but it will always tell you. But for now, this is acceptable. Same thing. Let's convert 13 pi over 14 radians, which it doesn't say, but that's implied, to degrees. Similar process. We start with 13 pi over 14 radians. And I want the unit of radians to cancel this time because I want to be left with degrees. So I'll put the radians conversion factor in the bottom, which is the pi. And we know there are 180 degrees and pi radians. Plugging this into my calculator, I get that this is about 167.143 degrees. Are there any questions on how I did either of these? Cool. And just to make it very clear, all we used is the conversion rate that pi radians is 180 degrees. That is all you need to do these conversions. Okay. So radians and quadrants. So just looking at this, well, first of all, if you've never seen this before, this is the Greek letter theta. And theta is often used to denote angle measures. So when you hear me say theta, I'm usually referring to this guy. And 90% of the time in this class, when we were talking about a single angle in radians, we will be using theta. Greek letters are often used to denote angles, and theta in particular with radians. Okay, so if you've never seen these before, you probably did in college algebra. These are the 4 quadrants: quadrant 1, quadrant 2, 3, 4. Think about them starting in the positive quadrant and then going counterclockwise around. This may be a helpful diagram to have in your notes, and you will have it in your notes once you have the course packet for sure, but keep this in mind. And radians follow really nicely from how the quadrants work. So since the entire circle is 2 pi radians, it makes sense that each of the quadrants, which is a fourth of the circle, make up pi over 2 of them, because 2 pi divided by 4 is pi over 2. So the first quadrant starts with angles with a measure 0 radians and goes up to make angles with a measure of pi over 2 radians. Then once you're in quadrant 2, those are angles with a measure greater than pi over 2 radians and less than pi radians, because this is pi radians right here. And then once you get into quadrant 3, it is angles with a measure greater than pi radians but less than 3 pi half radians. Quadrant 4, greater than 3 pi halves radians and less than 2 pi. This will be important to memorize. Are there any questions? Okay, and just again, degrees have a sign to designate that they are in degrees. So if you see a degree symbol, it is in degrees. However, if I just say, hey, this angle has a measure of 6 pi over 8 and no degree symbol, you know it is in radians. Unless there is a degree symbol, the angle measurement will be in radians. That will be true for the entirety of this class. Okay. So moving on, standard angle values. This is unfortunate that we don't have the course packet. There is a page called Standard Angles and Points on the Unit Circle. I will upload this to WIO courses because it is important for you to have, and you don't have it yet. And there's also something called the Unit Circle. This will be the most important piece of reference in the entire class. I'm not joking when I say that. You will need to know the unit circle. And I have a copy of it just right up here. This is what it looks like. It has all of the degree measures and their equivalent radian measures. So for example, 30 degrees is pi over 6 radians. And then it tells you, this is a circle with radius 1. It tells you what point on the XY axis this lies on. I'll get into more about why this is important later. But you will need to memorize this as quickly as possible. In a normal semester, you would have a quiz on it that you would probably have to take many times until you got a very high score. But unfortunately, we are not in person and it is very hard to do quizzes online. So just know I cannot stress the importance enough of how important this guy is. I will upload an image of it as soon as class is over, but please, please study this. It will make your life so much easier when doing work and when following lecture. Okay, so back to where we were, and there's some other reference pages up here. You won't need any of these for now. You will just need the unit circle. You will get all these reference pages with your course packet when those show up. Also convenient about this unit circle, it gives you the negative angle measures. So notice here it has 11 pi over 6, which is the angle measure if we would be going clockwise or counterclockwise around. However, if you go clockwise, it's also negative pi over 6. And I will talk about those more later too. But just understanding this circle will be very beneficial to you. Okay, so back to where we were. You will need to know this, moral of the story. Okay, so now let's get into more of what a radian actually is, because we've worked through the conversion of it, but it's still this arbitrary thing that we don't really know what it is. We know what a degree is. We know that a degree is just how every single circle is broken up. The size of the degree is the same regardless of the size of the circle. So what I mean is we could have a circle that's this big, or we could have a circle that's this big. The size of a degree does not depend on the size of the circle. That's a little bit different for radians. So what exactly is a radian? So the formal definition I give here is that you are dividing the circle into segments as long as the radius of the circle, and you're counting them. So what do I mean by this? So let's take an arbitrary little circle here. And if you remember, the radius is just from the center to any edge of the circle. Let's call it R. So by this definition, what we're saying a radius is we're taking whatever the length of R is, and we're going that length around the circle. So this right here would be 1 radian. And then we will go the length of R again. And then that's another radian. Obviously, this is not entirely to scale, but 1 radian is just 1 radius. English language works out nice sometimes. Latin is beautiful. But yeah, so just remember that 1 radian is 1 radius of the circle. And obviously the size of that radius changes depending on the size of the circle. Smaller circles are going to have smaller radii. Therefore, for that circle, a radian will be smaller. However, it still nicely works out that every single circle, it takes 2 pi radians to go around. Why is that true? Well, if you remember from geometry in high school or maybe middle school, the formula for the circumference of a circle is 2 pi r. If you remember, hopefully you remember that. If not, cool. But that's the formula for circumference. It's always been true. You just take 2 pi and multiply by the radius. Okay, well, how many radii are in a full circle / rotation? So if we draw our little circle again, say it has a radius length r, and we start going around, how many of these little segments of length r are there? Well, we know that there are 2 pi radiuses to find the circumference. So circumference is 2 pi r, and 1 radius is just a radian. So how many radii are in a full circle? There are 2 pi of them, because there are 2 pi radii in the circumference. And that's all when we say full circle / rotation. That's just talking about the circumference. That's just another way to say circumference. So there are 2 pi radii in a full circle. Convenient. That's exactly what we said a couple slides ago. Up here is that there are 2 pi radians around a circle. Math works out sometimes. It's nice. Okay, so let's do a little problem just to flex our knowledge a little bit. So if my circle was of radius 2 centimeters and I went 3/4 around the circle, how far did I go in centimeters? Well, I like pictures, and pictures always helps. Let's draw a picture. Here's my circle right there. And we don't have to label the radius with r this time because we know for a fact that it's 2 centimeters. And I want to go, let's say this is my starting point. I want to go 3/4 of the way around the circle. So I want to do one of these. How far is that? Well, it may help first to find the circumference. So just using this formula over here, I know that the circumference is 2 pi times our radius, which is 2 centimeters. So the circumference is 4 pi centimeters. This is one circumference here. However, I only want to go 3/4 of the way around the circle. I don't want to go the whole way around the circle. I don't want to do one circle. I want to do 3/4 of the circle. So then we just do 4 pi centimeters times 3/4, which, doing some quick math, is just 3 pi centimeters. And that's your final answer. The full circumference is 4 pi centimeters. So intuitively, we know that if we only go 3/4 of the way around, we will only be going 3 pi centimeters. Any questions? Nope. Okay. Then let's move on to arc length in general, which is essentially what we just did. But let's talk about how we would find a general arc length. So theta is always in radians. This is always true unless otherwise stated. I will just make a note here to emphasize that point even more. It is always true unless otherwise stated. Okay, so I want to find the length of S, which is this arc. It's just an arbitrary arc. It doesn't have a number. It's just whatever we want it to be. And we want to find the length of S in terms of the radius, which is R, and the angle in radians, which is theta. We don't want the angle in degrees. Our angle will always be in radians when we're trying to find this arc length. So the question we're trying to answer is, given a radius R and an angle theta in radians, how can we compute S? Well, we know for a fact that theta in radians is just the number of radii in the arc. So we don't know what the measure of the arc is in the unit we want, but we do know how many r's are in S because that is given to us by theta. So how do we compute that? That's just division. We know right now, we know that theta is just the length of the arc, so the number of radii divided by the size of the radius. We know that just from knowing that S is the number of R, or no, that theta is just the number of R. That gives us that ratio. So doing some quick multiplication by R, we get that S is R times theta. You can think about that either way. You can think about S being the number of R times theta, or you can think about it this way. Either formula works, but theta just gives us the number of radii in the arc. So that just gives us a ratio, which we are then able to solve for S. And as a note, this may come up later, units are important. Units of S and R always need to match. You can't be working with an arc length in feet and a radius in centimeters. It just doesn't make sense. The units will get confuzzled. So when you're doing these problems, you always need to check that your units of R and S match if those are the two things you were given. You also need to check that theta is in radians. Trying to do this with theta in degrees will not work because what's so special about theta is that it gives us the ratio that theta is just the number of radii in the arc. That is why we need radians for this, because degrees doesn't tell us anything about this radius or the size of the radius or how many radii there are. So we will always need that angle measure in radians. Any questions? These are the two important formulas we'll be taking with us. They're the same formula. They can be derived from one another. But this, if you can rederive this ratio in your head by just remembering that theta is the number of radii in the arc, you're golden. Okay. So let's do a couple examples. If we're given a sector with a radius 19, and a sector is just kind of a wedge in a circle. So I'll start drawing the picture. So if that's the center, we'll say this and that. This guy right here is the sector of the circle. That's just a fancy word for that. So given a sector with radius 19 centimeters, I'll just label that right now. We know that that's 19 centimeters long and an arc length of 8 centimeters. So we know that this guy is 8 centimeters. Find the subtending angle. And that sounds like a big word. All it wants is theta. That is all it is asking for. The subtending angle is just the angle that produces a sector. That's all it is. And you will probably not see that word pop up too much, but if you do, it's what you think it is. It's the angle that we talked about on the page prior. Okay, so what do we know? We know that we are going to need from this page up here, somehow we need theta, S, and R. So theta equals R equals S equals. So what do you have? Well, we have that the radius is 19 centimeters and that the arc length is 8 centimeters. And the arc length is not theta, the arc length is S, so we know that that is 8 centimeters. So this is what we want. This is our unknown. We are solving for theta. Conveniently, we have a formula for that. Theta equals S over R. All we have to do is plug in S and R into this formula, and it will give us our angle in radians. Math is beautiful. Okay. So plugging things in for S and R, we get that theta is equal to 8 centimeters, which is S, over 19 centimeters, which is R. Luckily, both of our S and R are already given to us in centimeters, so we don't need to do any other conversions there. If it was given to us in other units, we would have had to do a unit conversion before we solved for theta, but we don't have to do that in this case. Units of centimeters cancel. So we're left with that theta is 8/19 of a radian. You could also plug this into your calculator to solve 8 divided by 19. I don't feel the need to do that because 8 over 19 is already a pretty nice answer, but you could plug this into your calculator if you want to. Okay, let's do another one. This time we are given a sector with an angle of 37 degrees. That's the same as the subtending angle, and an arc length of 20 meters. Find the radius. Okay, so let's draw ourselves another picture. Here's this, here's our radius. Let's draw that. We know that this guy right here is 37 degrees. And we know that the arc length, the length of this guy right here, is 20 meters. Okay, so my gut instinct, of course, like last time, is just to use this formula. Theta equals S over R. We can't do that yet. And hopefully we can see right away that this symbol right here is a red flag. We are not allowed to have our angle in degrees. So how do we fix it? Well, we just turn it into radians like we practiced a little bit earlier. If you recall, the conversion factor for angles to radians is that for every pi radians, we have 180 degrees. That's the conversion factor. So we need to start by converting 37 degrees into radians. And to do that, just like last time, we start with 37 degrees. We want the units of degrees to cancel. In order to do that, we have the degrees on the bottom, 180 degrees per pi radians. And this is about 0.64577718. I put a lot of decimals there because I didn't want round off error. These kinds of problems are where it's extremely helpful to have a calculator with memory, so you don't have to work with rounding or rounding error. You can just type this in the calculator and then leave it there and use that answer. But if you have to round, that's okay. So that is about how many radians are in 37 degrees. And now that we have this, we need to find the radius. So we have the formula that theta is the arc length over r. So in this case, what do we know? We know that theta is equal to 0.64-ish, and we know that S is equal to 20 meters. We are solving for R. So let's plug this into our formula. So we have that 0.64 is equal to S, which is 20 meters, over R. I want this R out of the denominator because it's not doing us any good there. So then we multiplying both sides by R, I get that 0.64 R is equal to 20 meters. Again, I want R by itself now, which I can do by dividing both sides by this 0.64 here. So that gets us that R equals 20 meters over 0.64. We know that's radians, it's implied. And when I do that division, I get that R is about 30.97 meters. So essentially all I did was I took the angle, I converted it into radians because we need that for this problem, and then just took that radian measure, plugged it into our formula with the arc length, and solved for the radius. Are there any questions on this one? Nope. Okay, so then this is just a nice diagram to illustrate what I was talking about before. There are 2 pi radians in a circle, and we know pi is 3.14, so it makes sense that there will be a little more than 6 radii in a circle, because 2 times 3.14 is a little more than 6. So you'll notice we go 6 radii. This is the radius here. We're just going around 6 of those around the circle until we get here. So it's a little more than 6 radii to go around the circle. This is a helpful picture to have in your mind of what a radius is. Just know, I'll make a note here. 2 pi is approximately, I believe, 6.283-ish. So, and that's about how many radians are going around a circle. So this is a nice picture to have. Okay, so we talked about arc length of a sector. So let's talk about area a little bit. So first we'll start by completing this little table just to get an intuitive sense. This just a little bit of review of geometry. So if we think about the full circle, how many radians are in a full circle? 2 pi of them. And what is the area of a full circle? In other words, what's the area formula we've been taught since geometry? It's just pi r squared. Nothing fancy, just the formula we've been taught, the formula you can Google whenever you need to. It's just pi r squared. Okay, now let's think about half of a circle. If 2 pi radians is a full circle, we know that there are pi radians in half of a circle. So then we can also divide the area by 2, and that the area of half of a circle is pi halves r squared. Let's keep going. If a full circle is 2 pi radians, then the angle for a third of a circle is 2 pi over 3 radians, just dividing by 3. And I will do the same thing over here. If the area of a full circle is pi r squared, the area of a third of a circle is pi thirds r squared. Same with a fourth. We divide 2 pi by 4, we get 2 pi fourths, which is just pi over 2 radians. And then we would divide the area formula by 4 as well, and get that their area of a fourth of a circle is pi fourths r squared. Just doing division, cutting the circle up. Okay, what about an arbitrary angle theta? What if I just give you any angle? We're working with any angle in a circle. What would the area of that part of the circle be? What would the area of that fraction of the circle be? Well, notice that if we have 2 pi radians, if that's the angle, then it's pi r squared area. If the angle is pi radians, it's pi over 2 r squared. If the angle is 2 pi thirds, we divide it by 2 to get pi thirds r squared. If the angle is 2 pi fourths, we divide that by 2 to get pi fourths r squared. So in general, if I say your angle is theta, the area of that sector will be theta over 2 r squared. And it makes sense if you think about it. You could just replace theta, pi with theta for any of these comparisons here, and it works. So in general, if I say here is a sector of a circle with the angle in radians being 5 pi over 6, you know, you just be able to divide that by 2 to get the area formula for that sector. So what I mean by that is the area formula for a sector of a circle is just theta over 2r squared. You're given theta, and so that's the area formula. Instead of just pi r squared, we use theta. Okay, so using that information, let's do a brief example. I want to find the radius of a sector of a circle with a central angle of 60 degrees and an area of 10 inches squared. The central angle is still just the angle we've been working with. Nothing special there. So here's a circle. And I want to solve for the radius right here. I know that this angle right here is 60 degrees. And I know that the area of this little chunk right here is 10 square inches. Okay, well, what do I know here? I have this formula here with 3 unknowns: the area, the angle theta, and the radius. So let's plug in what I know. I know that A equals theta over halves r squared. I know the area. I know that the area is 10 inches squared. And I know that theta is 60 degrees. However, I would like to work with theta in radians because I need to for that comparison with the radius. And I actually don't even need to do math to know that theta, that 60 degrees is pi thirds. This is one of the key angles on the unit circle you will need to memorize. 60 degrees will always be pi over third radians. You can do the conversion to confirm this. However, this will be an angle that hopefully pretty soon you will just be able to recite and know right off the bat. But just know that because this is in degrees, we need to convert it to radians, and 60 degrees is pi third radians. And we don't know r. Okay, so let's plug these into this formula. We know that 10 inches squared, because that's our A, is equal to theta over 2, and theta is pi thirds over 2, and we don't know r. So that's just r squared. I just need to solve for r now, just some algebra. Let's just dividing this by 2 to make our lives easier right off the bat. We know that 10 is equal to pi thirds divided by 2 is pi over 6 r squared. I want r squared by itself, so I'm going to divide both sides by pi over 6. This gets us, by using some fraction division, to that 60 over pi, because I just had to invert and multiply. I did 10 over 1 times 6 over pi. That's how you do division. You take the second fraction and just flip it upside down. So I got 60 over pi is equal to r squared. And now I just need to take the square root to get r. So that gets us that r is equal to plus or minus the square root of 60 over pi. You can plug this into your calculator. I'm not going to right now. I think it's okay as is, but this will be your answer. However, I only put the plus or minus there because when you're taking the square root, you should always intuitively do that because there will always be 2 answers. However, we're talking about a tangible circle with a tangible radius, and it just does not make sense for a radius to be negative. It literally just doesn't make sense. If I hand you a circle with a radius, with a length with a radius, it's not going to be negative. So in this case, we do not need to worry about the negative case, but you should still always intuitively make that mental check, because sometimes when working with square roots, you will need both answers. So our final answer is just the square root of 60 over pi. Are there any questions on how I did that? Okay, I think I'm going to stop a little early this time because we are getting into a new topic, which is using all of this new vocabulary and conversions we just learned to do something called angular speed, which is talking about when we rotate a circle, how quickly are things going around, and linear speed, which talks more about distance. And we will talk about this more on next time and start working on some triangle trig. Are there any questions on anything that anyone has? Okay. I'm going to stop the recording after this. If anyone has any questions, feel free to stick around. I will stick around for a few minutes to chat if anyone needs to. Otherwise, have a wonderful Tuesday, and I'll see you all tomorrow. Please do your initial knowledge checks before the end of the night and sign into your Alex. I will be answering my email all day if you have questions. They are due tonight, though. The initial knowledge check is due at midnight tonight, and it is just participation. So please do that.